So the topic of my presentation is time optimal control on a subspace. I am Oleh Vozniak, and my supervisor is Doctor of Science in Physics and Mathematics, Professor
Oleh, could you please speak louder?
Okay. I will increase the volume of my microphone. In this presentation, I will explain the problem of time optimal control on a subspace and give the solution for this problem has the form of piecewise function with n-1 switching points. And here I will show the equation obtained for the difference between the switching points and the total time theta in two different methods, using the optimization approach and using the proposed by Pantrianin transversality conditions. So the problem of time optimal control on the subspace is formulated in the following way. Here we consider the canonical system, but it can be any system with constraints on the control u lesser or equal than 1 from some point x0 of the space onto a subspace given by some equation matrix H multiplied by X equal to 0. In this presentation, we will tell about the subspace which of dimension n-1, that is a hyperplane. First, I will start with the problem of optimal control into the point. If we have a linear system in the following form, it is a non-homogeneous linear system, and thus its equation, its solution can be written using the Cauchy matrix K, which for linear system is the exponent of matrix A. Then the xt can be written as in this form, and for the time moment of time theta, we can rewrite this in the following way. So our task is to find the control U of t, which minimizes the time theta to solve this equation. Now I will tell about the Pantrianin's maximum principle. For this same system, it is proven that the optimal control y stars must satisfy the following equation, where the function psi is the solution of the adjoint equation dot psi equals minus a transpose psi t. In our case, matrix A and B have the following form. So the system of equations for psi are the following: psi n equals 0, and other psi's are minus previous psi. So we can write that psi n is some constant Cn, psi n minus 1 is some linear function, and psi 1 is some function of the degree n minus 1. If we recall this equation, matrix U multiplied by vector B is going to be psi 1, and to maximize this dot product, matrix U must be positive when psi 1 is positive and negative when psi 1 is negative. So U is a signum of the psi1 of t, and because psi1 is a polynomial of degree n-1, function of t must have not more than n-1 switching points. Let us call it t1, tn-1. Then this equation becomes a system of equations for t1, tn-1, and the optimal time theta, where ck are given by this formula. Now let us this equation has been solved by Валерий Иванович Коробов and Григорий Николаевич Sklar, and it was solved using the moment mean problem approach. In this work, we consider the problem of control onto a subspace. We consider the same with linear system, and subspace, we will write the subspace in the form of k1 x1 plus k2 x2 minus xn. Then the endpoint xt can be written in the following way. Thus, we obtain the optimization problem. We want to minimize function theta under the constraints of this form. This is the same equations, but now the right-hand side also depends on the endpoint x1, x2, xn-1. So we have optimization problem with two n-1 parameters. One parameter is theta, and n-1 switching points, and n-1 parameters defining the endpoint. One of the approaches is to consider the method of Lagrange polynomials. Then the function is theta plus sum of lambda I multiplied by these equations. Now we take the derivatives of theta, of L, and tk. And what is interesting that the equations for tk do not are all in the same forms, because they only thing that changes is this sign, but we make it equal to 0, so the sign doesn't matter. And from the first two, from the system and from this equation, we can obtain the values for lambda y, and if we put them into the equations for tk, we obtain the following equations for each ti, because they are the same. Ti minus theta times n-1 plus the sum equals to 0. As we can see, all these terms have the difference ti minus theta, and if we replace this with some variable t, we have the equations for switching points. These switching points must be lesser or equal than theta. Therefore, the maximum number of switching points is equal to the number of negative roots of the equation 1. It should be noted that from this equation, it is not clear where this roots are consecutive or some of them are omitted, because the optimal solution can be either in the switching points or on the bounds of interval when, for example, T2 equals T1, and we have less than n-1 switching points. But it shows that the maximum number of switching points is this value. This example is for canonical system of degree 2 onto a subspace x theta alpha k alpha, where k can be any real number. Let U be -1 on the first interval, then we can obtain this system. Here we don't use method of Lagrange multipliers, we can just write the derivative for alpha and obtain that T1 equals theta minus k. Thus, when k is positive, T1 is lesser than theta, and we may have one switching point. And when k is negative, we have no switching point. This is example for n minus or n equal to 3, when we may have two switching points, one switching point, or no switching points at all, depending on the parameters k1, k2 of the subspace. Another approach is to use the transversality conditions. We again consider the same canonical system. Psi1 are given in the same way, and control also the same. Transversality conditions says that the function psi must be orthogonal to the given plane in the endpoint t equals theta. Therefore, we have that psi1 of theta. It can be written in many ways, but here we will take the vectors 1, 0, 0, 0, k1, 0, k1, 0, 0, k2, and then this condition can be written as psi1 theta plus k1 psi theta equals 0, and for all other functions. Then we obtain the following system of linear equations for the variables c1, cn. It has n-1 roots, so we can express variables c1, cn-1 as functions of variable cn. And if we recall that what t is this signum of the sum, then what t is signum of cn times the sum divided by n-1 factorial, which is the same equation as we obtained using the optimization approach. But this condition is even stronger because it says that no switching points can be omitted because they will depend, they will affect the signum of function O from t. This is the example for n equals 7. Here we chose specifically k1, k2, k7 in such a way to roots of the polynomial be from 1 to 7 to 6. Then we cannot show the trajectory, but we can, for example, consider the distance between the point and the plane and show that it reaches 0 with given control. So the conclusions. Time optimal control on a subspace has no more than n-1 switching points. It can have less points depending on a subspace. If the switching points ti exist, then the difference must be the roots of this polynomial. The topics of the further research is to determine the sign of the control on the last interval, exact number of switching points, and the equation for the optimal time theta, because this equation is only for difference, and if we're using it, we need also then make some other steps, such as consider at first control with 1, 0 switching points, and with 1, then so on for n minus 1. This is all. Thank you for your attention. I'm ready for your questions.
Thank you for your presentation. Please, Professor Polski.
Thank you for your talk. I have a couple of questions. First is a little bit philosophical, or just to clarify the problem. Do you use the subspace only for initial condition of your problem, or you require the whole solution is located into this subspace?
I require that we start in any point, but we want to end on this subspace in.
You want to come back to this subspace, right? From any point to this subspace.
Yes.
And one more question.
Not to come back, just go to not
come back. But maybe come back, maybe yes, I see. And one more question, please, concerning your main equation, number 1. What if this equation has complex roots? You require, say, is equal to number of negative roots of the equation, but the equation can have complex roots. What can you say in this circumstance?
Then they will not affect the number of switching points, because it means this equation essentially that the control changes the sign when we so we have some function of t, and control will change the sign when this polynomial comes through 0. So if polynomials are complex, we don't have the change of sign of the function t and of the control u.
So as I can see, the complex roots has no effect to this how do you say the switching points.
Yes.
So if the polynomial has only complex roots, then there is no switching points.
Yes.
Thank you.
Thank you for questions.
Thank you everyone for questions, and Oleh for presentation.